Welcome to the Math 1, Unit 7, Lesson 3 summary video, Children's Barnyard Revisited. This lesson is a develop, solidify understanding task, which is meant to both introduce you to a concept and help you formalize those ideas. The purpose of this lesson is to use area models and/or algebra tiles to help develop and solidify the understanding of multiplying two linear expressions and adding two quadratic expressions. The North Carolina State Fair Planning Committee is still working on plans for the children's barnyard. They need to rebuild the barnyard using new dimensions. In order to begin, the committee will start with the duck pen. Let X represent the dimensions of each side of the duck pen. You can see the diagram here on this screen. The first question says, what is the area of the duck's pen? Well, we can tell that this is a square, and we know that in order to find the area of a square, we need to take the side length and square it, or multiply the length times the width. In this case, because they are both x, because it's a square, we can simply replace the s for side length, and in its place, we can put in the actual side length, which is x. So we know that the duck's pen is going to have an area of x squared. We're going to use this information and this original duck pen and its area to answer all of the questions remaining in this lesson. Question 2 says, now let's draw a diagram to represent the area of the cow pen. If it starts as the same size as the duck pen, but is increased by 4 feet on one side and 3 feet on the other side. So we're going to increase the side length of x by 4 feet on one side and by 3 feet on the other. So if we increase one side length by 4 feet, it's going to extend out this way, and we have x here, and we extend the other one by 3 feet, we know that if this entire side length is x plus 4, then this entire side length has to be x plus 4 as well. And if this entire side length is x plus 3, then we know that this entire side length is also x plus 3. So we're no longer going to have a square, but now we're going to have a rectangle that's x plus 4 feet on one side by x plus 3 feet on the other side. So we're going to look at these algebra tiles now, or look at this model for the cow's pen using algebra tiles. If you don't have access to algebra tiles, don't worry, you can draw this diagram yourself. You would just start out with a square and label each side length of the square x by x. We then determined that we were going to extend the side length of one of the sides by 4 units. And so we're going to use these rectangles here to add on, because I know that if this side length is x and I'm adding 4 feet, I'm adding a foot, adding a foot, adding a foot, adding a foot, then the dimensions of each of these rectangles will be x units long by 1 foot. This side length is x because this side length of the square is x. And then here we're adding 1 foot. And so the dimensions of each of these would be x by 1. So the area of each of the rectangles would be x. So we're going to put all of these rectangles here. And again, this now represents x plus 4. We added 4 feet to the length of x that already existed. And so then we're going to do the same thing up here. And we're going to extend each of these. Only need 3. And so the area of each of these rectangles would be x as well, because the dimensions of each of the rectangles are x units by 1 unit, and 1 times x gives me x. Next, we are going to fill in this empty space with each of these unit tiles. And the reason why we have to fill these in is because we know that if this side length is x plus 3, then this entire side length also needs to be x plus 3. And so creating this rectangle so that the right side matches the length of the left. Same thing here. If this is x plus 4, then I know that the top portion also has to be x plus 4 in order for this to be a rectangle. And so when I fill these in, notice that each of these unit tiles has 1 on it. The reason why they each have 1 is because for my rectangles, this side length is 1 unit, 1 foot, so that means that this side length is also 1 foot. So the bottom portion of each of these unit tiles is going to be 1 foot. Same thing over here. If this side length is 1 foot for each of these rectangles, then I know that this side length is also going to be 1 foot, 1 foot, 1 foot. And so for my little squares, their dimensions are 1 foot by 1 foot, which gives me 1 square foot. So if I want to find the combined area for this entire figure, I know that in order to find the area, I've got to multiply my length times my width. And my length here is going to be x plus 4. So I'm multiplying x plus 4 times this side length, which is x plus 3, and I can do this one of two ways. If I have an area model, I can simply combine like terms in order to determine the area of the entire figure. So I'm going to start with my variables. They're going to come before my constants, and I will start with the variable with the highest exponent. So that would be my x squared. So I have one space that has an area of x squared, and then I have 1, 2, 3, 4, 5, 6, 7 spaces that have an area of x. So I have 7 x areas, and then I have 1, 2, 3, 4 by 1, 2, 3, so that's 12. I have 12 units that have an area of 1 square foot. So this would be the way that we would represent the area for this enclosure. I could also look at this in terms of the distributive property. And so we know that if I didn't have this x plus, if all I had was 4 times the x plus 3, I would simply distribute the 4 to each of the terms inside the parentheses. Well, here I have 2 terms in my first factor, and so I'm going to distribute each of those to each term in my second factor. So I've got x times x, which is x squared, plus x times 3, which is 3x. Now I've got to distribute the second term to each of the terms in my second factor. So I've got 4 times x, which is 4x, plus 4 times 3, which is 12. Next, I'm going to combine my like terms. So I'll combine the 3x and the 4x, and you can see how we get from here down to here. So I've got x squared plus 7x plus 12. You'll follow those same strategies for problem number 3, where you'll be finding the area of the sheep and goat pens using the area models, and you'll, again, for each of those, you'll be starting with this original cow pen, which is, duck pen, which is x by x. Number 5 asks us to find the area for each pen given that the value of x is 5. So there are 3 different ways we can go about this. We can substitute the value of 5 in for x into this equation, and we get 9 times 8, which is 72 feet squared. And we can substitute it into our trinomial here, 5 squared plus 7 times 5 plus 12, and we get 25 plus 35 plus 12. 25 plus 35 is 60, plus 12 is 72 feet squared. And finally, we can use our area model to help us. Again, substituting in that 5 for the x's. So x squared would be 5 squared, which would give this an area of 25. And then for each of my x's here, I would have an area of 5. And so if I add up all of these areas, I've got 25, 30, 35, 40, 45, 50, 55, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72. So using the area model, I also get 72 feet squared. Now we're going to look at problem 6a. They are taking the original duck pen and they now want to create a new cow pen, but they realized that the previous plan was too large and so they want to make it smaller. So they're taking the original area of the duck pen, x squared, and they're going to extend one side by 5 feet and they're going to reduce the other side by 3 feet. So this is the same as the previous example. We're just adding 5 units, 5 positive 1 to the side length of x. Each of these represents 1 foot, and we know that the other dimension is x, so it's x by 1 gives me x. On the other side, we know that the longer side length is still positive x, but now that we're reducing the x squared, the x side length here by 3, the smaller side lengths of my rectangles are going to be represented with a -1 because we're taking away 3 feet. So that gives us an area for each of these rectangles of -x. We have a side length of positive x by a side length of -1, which gives me -x. And for each of my smaller squares, I've got a side length of +1 by a side length of -1, which gives me an area of -1 for each of my smaller units. We can use the distributive property, just like we did in the previous example, to come up with this equation for our area. We can also use our area model to combine like terms. So we're starting with that x squared, which we see here. Then we have 5 positive x's and 3 negative x's, which leaves me with 2 positive x's. Then I have 15 negatives, which you can see here in this last term. And finally, we will look at problem 6c, which is a new goat pen, and they're taking the original duck pen and they are reducing this side length by 5 feet, and this side length they're reducing by 3 feet. So we know that each of our rectangles on this side would be a -x, have an area of -x because we've got positive x by -1, which gives me -x. On this side, each is a -x because we have positive x by -1, which gives me -x. And then for each of my smaller units, I've got a -1 times a -1, which gives me a +1. So each of these would be positive. And we can, again, see how that's represented in using the distributive property. We've got x times x, which is x squared, x times -3, which is -3x, -5 times x is -5x, and negative 5 times negative 3 gives me positive 15. We combine these like terms to give me negative 8x plus 15, and again we can use our model to come up with this same equation. We've got x squared, which is positive, plus 1, 2, 3, 4, 5, 6, 7, 8 negative x's, or negative minus 8x, plus 15.